Uh, Welcome to the afternoon session. I guess the plan for today is to have like two talks, a break, then another talk, and then like a reception and a poster session, which will happen simultaneously. I mean, the reception and the poster session will happen on the second floor, like at the time when the schedule says. Yes, one thing, like doors to the second floor are gonna lock at 5 p.m. So like we'll need to like open them for each other or something. Anyway, so the first talk is Ben Golub. Currently also with a hybrid talk.
Hybrid talk. All right, should I start? Yes. Thank you. So first, I think I'll say this again later, but Alex, I'm super grateful to be working with the whole team, but Alex in particular has done just an amazing amount of work to make this happen. And so I'm super grateful to him for involving me and for the opportunity to speak here. So this is work with work on pass-through and market power, a principal component approach with Galeotti, Goyal, Talamas, and Omer Tamuz, who is here. So this is a project about differentiated oligopoly, and I'm going to do something a little unusual and just start with one column of model because it'll be easier to do that, to explain exactly what I mean by the words differentiated oligopoly before I tell you what we do with it. So this is a game, a static game among n players. The players are called firms. There's also going to be a representative consumer. So each firm is identified with a single good that it produces. And the simultaneous move game is that firms simultaneously announce prices. Each price is its own good, which leads to a vector P of everyone's prices. And then the consumer is going to choose, seeing those prices, the consumer is going to decide how much to eat. The representative household is going to decide how much to eat of each good at these prices. And then the consumer has a utility function. I guess this is the one risk of the model on the first slide. But it's going to persist for a while. So the consumer is going to see these prices that the firms have announced and is going to decide how much to eat of each firm's good. So the consumer's utility function is quasi-linear in money over here. And it's just a value for eating the various goods, which in here we're going to be not impose many assumptions for now, at least, and say this is just a general a concave continuous function. Let's say continuously differentiable. And so that's going to determine the consumer's choice here. Maximizing this utility function with these prices is going to determine the quantities of all goods that are purchased, which is what these firms care about when they're setting their prices. And the way the firms care about it is that they're going to receive profits equal to the quantity of their good that the consumer chose to buy times their unit profit, which is price minus a constant marginal cost. I don't really need constant marginal cost, but I will assume it to keep things a bit simpler. So for those who walked in late, I think the only important thing you didn't hear is that at this stage, before anything else happens, firms simultaneously decide how each is going to price its own good. And each firm has a proprietary right to produce good I. So firm I produces good I, chooses the price for that, and then the consumer eats, and then the consumer gets this payoff, and the firms get these profits. Any questions? This is a mistake. So I would write minus M here, but here I even know how much money the consumer spent, which is just P dot Q. That's the amount that it costs to buy these different goods. Yeah, so I should really just say this, there should be no M here. It should be C of Q. Thank you. Other questions? So that's a very simple kind of canonical differentiated oligopoly pricing game. And you can see pretty quickly from this setup that there's going to be fairly rich strategic interactions here because when I change my price, and therefore the amount of my stuff that the consumer eats, it changes your demand curve. So my price matters for your pricing problem. So that makes these firms strategically entangled. Now we know that this outcome, there's going to be interesting normative questions here, because this kind of game is not going to lead to efficient outcomes. It wouldn't be efficient if they were independent monopolists, each selling their own thing. And that's not really going to change when their demands get entangled. These market power effects and their normative implications have been of great interest to several recent applied literature. So for example, Bakai and Farhi show that these kinds of market power distortions make a big difference to aggregate GDP, if you want, in a disaggregated rich macro model. Verstein and co-authors show that market power effects and varying wedges or distortions over time make a big difference to the analysis of macroeconomic time series. And then Pellegrino, in a recent paper, uses a calibrated version of this style of model, calibrating it to the whole US retail market to show that market power distortions are a big deal, eat up a lot of the, have a 20% welfare cost to the US consumer or something. So applied people are interested in these differentiated oligopoly type of problems. And what we want to do here is do a fairly humble, I think, microeconomic exercise, which is just the comparative statics of this differentiated oligopoly. So I'm going to specify an exogenous, what I'm going to do is I'm going to introduce a dummy parameter xi, which I just used to move around the economy. Think of it as starting at 0. I'm going to specify costs exogenously as a function of xi. So this just gives me a way of defining a movement of the exogenous parameters, which are the costs. And then for any other variable in the model, typically the endogenous ones, I'm going to write x dot to say how that thing moves as I move around this exogenous, when I move around the cost exogenously, everything else is going to react, and x dot tells me how x reacts, where x is price, quantity, welfare, whatever you might be interested in. And a particular object of interest for us is going to be pass-throughs, which is how a given change in costs affects equilibrium prices. So price pass-through is how much a change in costs affects prices. Welfare is how much it affects welfare. Okay. And what we're going to offer is a principal component perspective on pass-throughs, which is going to give us a new way of writing out the comparative statics and saying which cost shocks matter most, in a sense, for price and welfare volatility. That's one thing we can do. That's kind of a physics exercise. And maybe more in a stacked on top of that will be a policy exercise, which is so this uses an idea going back to Marshall that you can use small taxes to shine a light on the distortions in your economy. You can understand the distortions in your economy by asking, what's the first little unit? If I had a little unit of tax power and subsidy power to try to remedy it, what's the first unit of intervention I would do? That kind of tells you where the distortions in your market are. And so we're going to study a stylized problem of that type in order to say what the distortions are in these entangled oligopoly systems. And we'll find that the principal component analysis is a useful way to look at it. So that's the 10,000 feet overview. And now I want to tell you what we actually do. We're going to assume existence of, it's not hard to guarantee it. We're going to assume existence of an interior pure strategy Nash equilibrium in prices. And we're going to look at it, and then we're going to study how stuff moves around by just basically differentiating the first order conditions, right? So we're going to look locally at how this particular equilibrium of the game moves around as we perturb the costs. So firm's first order conditions, I've just written them here. They're not so important, but I thought it would be. So this is when you just take firm I's profit and you differentiated it in its control variable, which is its price. And I should say here the subscript, like QI, is just firm I's quantity. It's not a derivative. Okay, so the only derivative here is this thing. And of course, the Q is induced from the demands from the consumer's demand behavior. The consumer is maximizing something, picks a Q. But once we have this Q, we can forget about everything underlying it and just say that's the demand function as a function of prices. So that's the consumer's first order condition. And now we're going to make a gigantic assumption. I'm going to assume that in some neighborhood, for all costs, or let's say for all prices, in some neighborhood of where we start, the demand function is exactly a linear function. So this is a terrible assumption. It's not true, for example, but it turns out that a lot of the forces I want to tell you about already appear in this case. And we've recently, and now I feel less bad about this whole thing because in the last couple of weeks, we've managed to understand everything without that assumption. And so it's not so important. I think we can, everything I'm going to tell you has a suitable analog without it, but I'm going to be able to tell you things more succinctly in this case. And with this assumption of linearity, I'm going to be able to define sort of something that's sufficient for something, a very important object that's going to kind of play the starring role in the talk, which is this demand derivative matrix, which is just the derivative, well, it's the derivative of firm I's cost in firm J's price at some P. So it's the same, it's the same thing that's written up there. And because I can measure the goods that the firms are selling in liters or ounces, I can assume that the own price demand effect is -1. That's just a normalization of the quantity measurements. So that I can get for free. And I am going to make that normalization. And after making that normalization, I can write down by implicitly differentiating these first order conditions in the perturbation that I am interested in, I'm going to be able to write down a formula describing how the prices change as the costs are exogenously perturbed, right? And so this formula is also worth writing down. So P dot is going to be equal to I minus D inverse. So that's the
Is your D now a D where the D is 0 on the diagonal, or is that?
It's a D where D is -1 in the diagonal, and then this matrix happens to have 2 on the diagonal, right? If D has -1 on the diagonal, this matrix has 2s on the diagonal. So at some level, maybe you could say we should stop here, because I was interested in the comparative statics of the system. Here they are. I can write the price effects as a function of the cost perturbation. And in this room, people have a good bit of understanding of what that thing means. So maybe we can stop. But I think if we stopped here, there would be insight left on the table about what is going on with these costs, how the cost perturbations translate into outcomes. And I want to convince you of that in the rest of the talk. I can just show you what I mean by saying that we can do better than just writing the answer like this. So let me try, especially for the tax policy kind of question. So let's try to say more. Let's try to extract more insight out of this formula is a way to say it. So let me remind you, but on the way there, let me just remind you of basic intuitions that you already have about price pass-through. So price pass-through says if your local bagel place has their marginal cost of a bagel increased by 10 cents, how much does your price change, right? So often in intermediate micro, we solve a basic monopoly with linear demand example. And there's a slope, when you solve that problem, you get a slope in your answer, which is a half. And that's the upshot of that, is that the price pass-through is a half. So if you have a little cost shock, it's going to translate the firm. If the bagels become 10 cents more expensive to the firm, that's going to be 5 cents more expensive for you, and the firm is going to eat the other 5 cents out of the other 5 cent loss out of its profit.
So right now it's the opposite, right?
It's their costs are rising.
No, well,
Oh, you're saying it goes up by more than one, or what are you saying?
in some cases it goes up by more than one.
Oh, you've been reading.
The cost of food for the restaurant is not going up by the factor the menu goes up.
That's an interesting claim. I don't know. The claim is that you have pass-throughs of more than one in the world now. I'm not sure that's true, but it's certainly not going to be possible in the model, although there are models.
And maybe a psychological effect that once the price go up, it's a good excuse to make more capital.
You're giving this talk in UC Berkeley, what do you expect?
Yeah, I'm mindful of the fact that I'm being recorded. So. If you have a competitive market, where price, so in a competitive market, imagine two bagel stores that face the same exact marginal cost, then Econ 101 says that you have price equals marginal cost. In that case, the pass-through is 1. Now, as we've seen in the formula that we've already seen, in a multi-firm oligopoly, pass-through isn't a number, it's a matrix, right? When any cost changes, everything changes. But this gives us some intuitions to grab onto, which we're going to be coming back to. But now I can tell you the core thought, I guess, of the whole talk, which is that we're going to look at the whole business in a different basis, which is a basis you choose based on the demand matrix itself. So this is where the representative consumer assumption actually somewhat matters. The fact that there's one representative consumer determining all the demands means that the demand matrix that I defined is a symmetric matrix. It's very closely related to the Hessian, so to the Hessian of this representative household. And so because D is symmetric, you can find a basis of eigenvectors that you can find the basis of eigenvectors of that matrix for the whole space, and these are orthonormal. So I can define a matrix U whose columns are all eigenvectors of D, ordered in some way we'll talk about later. Each of these U's is an eigenvector of D, and jointly these form an orthonormal basis for the whole space if you have 17 firms for R17. Okay, and the first thing that I'm going to do with this is for any vector you have in mind, for example, the vector of quantities, I can rewrite it by pre-multiplying by U transpose. I can transform it into this new basis of these eigenvectors. So in fact, I'm often going to talk about the vectors as bundles of goods. So you can think of each of these columns, if you're thinking in goods space, you can think of this as a bundle of goods, and this is another bundle of goods, maybe with negative entries. So rather than saying Christian's firm produces 1, and Matt's firm produces 2, I can say the production of the economy is 1 unit of the first eigenbundle, of the first eigenvector, and minus 2 units of the second eigenbundle. That's an equally good way, because these U's span the whole space, I can describe any consumption outcome in that way. And I'm going to be able to do the same thing for prices. I can in fact talk about the price of the first eigenbundle. That just means also transforming the prices into this new basis. So I'm going to be able to talk about a cost shock to the first eigenbundle or the second eigenbundle or a combination. And having set that up, I can tell you like the reason we're doing all this, which is that we can state this result. It's really a piece of bookkeeping. It says that once you've changed the basis in this way, you can write the effect on the price of the Lth bundle. You can write that effect as just a constant times the shock to the Lth cost in this new basis. So let me say it like this. If you have a cost shock that only affects the first eigenvector, a cost shock that's parallel to the first eigenvector, cost shock like this, then I can tell you exactly how it's going to affect the prices. It's going to affect the prices exactly in that direction in the eigenbasis. So if the cost shock is 1, 0, 0, 0, the price response is going to be lambda L 0, 0, 0, 0. So even though in the original basis, when I change a means cost, it affects everybody's price because of all these spillovers and interactions, in this new basis, it's just going to feed through in that same dimension, and there's going to be no cross effects of any kind. And moreover, this price pass-through, this coefficient lambda, which I call the price pass-through, is just some formula that I've written up there of the corresponding eigenvalue. So the first eigenvector had an eigenvalue here, and just some simple transformation of it tells me the price pass-throughs. So that tells me, I'll say more about this, but let me just, I hope the math is clear.
So if your matrix D would not be symmetric, you would have different left and right eigenvectors, and maybe you have a direction in the prices there, which will influence the direction in the cost there.
So if I didn't have symmetry, which I could lose, for example, by not having a representative consumer, I would have to do the way we're going to extend the same thing that we do is by using the singular value decomposition, which lets you have different bases for the costs and the prices. Okay, so I'm going to complete this slide, but before that, I need to define the thing, which I haven't defined. So beyond the price implications, I already anticipated that we're going to be interested in the welfare implications of a cost shock. And so I need to tell you what I mean by welfare. I'm going to make a very canonical definition of welfare, which is just a total surplus metric. So remember, the consumer had this payoff, the value of the goods minus the money the household pays for the goods. And the producers make these profits, these are the unit profits. So it's the dot product of each firm's unit profit times the quantities they sell. And so welfare is the sum of those. You can think of it, if you want a very concrete foundation, think of the consumer being a price taker when she shops, but then at the end of the day, all firm profits are ultimately rebated back to the consumer in the numeraire. So the household ends up eating that and being happy to, the profits in the economy are also valuable ultimately to the consumer. You could also study, incidentally, for, since we had some socialism over here, we can study we can do all of the exercises I'm going to talk about just caring about consumer surplus. That would be fine too. And I think economists' first instinct is to use this metric. So I'm going to tell you all the results for total surplus. Coming back to the result that I had already put up most of, the only thing I'm adding to it now is this welfare formula. So if I'm interested in how total surplus is going to be affected by this cost shock, I can write it as this formula which sums across the different eigenvectors. Okay, it's written in the eigen language, in the new basis that I've transformed into. So let's read this formula for welfare. It sums across these dimensions of these eigenvectors. This I'll read from the end. The Q at the end here says that for a bundle that the consumer is eating more of, obviously it matters more what happens to it. So when a bundle that is eaten in a large quantity will have a big welfare impact. And there's a minus here because when costs go up, nobody likes that. Everybody does worse when costs go up, they eat less stuff. So quantity matters. But what's maybe more interesting is that, and of course the size of the shock matters, C dot, and then the coefficient mu is what we call a welfare pass-through. It's a number that says, once you account for the proportionalities that I just mentioned, how important is this bundle? And it turns out that the welfare pass-throughs, so this is maybe the last thing I'll write up here. The lambdas are the price pass-throughs and the mu's are the welfare pass-throughs. And it happens to be that they're ranked oppositely to each other. So lambda is price pass-through. Over 1 minus, let's look back at the formula. 1 minus the eigenvalue, and mu is the welfare pass-through. And it's 1 minus the price pass-through. So I'll talk more about that's going to make more sense. I'm going to give some intuition for that. But the punchline is that we can write both the price and the welfare effects in a very succinct form. And if you think back to not doing this transformation, if you just wanted to do this in the original basis, you could, nobody would stop you. But for the welfare exercise, you would have this quadratic form thingy where you would have to worry about all the cross effects in, like when my cost is perturbed, it changes your price, that changes welfare so you have to worry about all these cross effects. When the system is diagonalized, you can somehow think of it as decoupled and look at it as welfare across as if independent pieces. And that's has its pluses. Of course, how good it is depends on how well we can interpret it. So because this is a short talk, I'm not going to be able to show you all of the payoffs. Go ahead.
Yeah, I have one question. So yeah, you started by saying assume you have linearity.
Yeah.
And now you're saying, oh, so then it decomposes nicely into eigenvalues and eigenvectors.
Yeah.
So then I have to go back to the original assumption. How realistic is that?
That has nothing to do with linearity. In the end, what the linearity was used to simplify the exact form of this implicit derivative. But if your system is differentiable, there's going to be some. So differentiability is a real assumption, and I don't think that's the
but then you will have linearity in a very small.
Yeah, you could worry about the second order terms.
Yeah.
I mean, let's put it like this. If you haven't understood the system's first derivatives, it's not time to talk about the second derivatives yet. So it's not, I mean, yes, comparative statics, you could always ask about further effects, but it's not a reason not to study the first ones.
I guess Amin's point is you will have something like the Hessian instead of theta.
It's, yeah, so if you wanted the way, I mean, yeah, the way the macro,
Like
so,
function of P.
yeah, so you could, right, this is absolutely true that the derivatives can only tell you about small perturbations. And if you wanted to understand further effects, you need to write down further derivatives. And as actually in macroeconomics with different economic assumptions people have done. Yeah, so I completely agree with that. I'm sorry, go ahead.
Okay, so in reality, sort of price shocks might actually appear in a different way, right? Putting my Stanford hat, you get inflation because everybody has more money and is less price sensitive. And so, but in reality, probably it's actually not some external cost where God changes the cost. It's probably either that the demand changes, consumers might be less price sensitive, or that the supply side changes, it's more costly to actually get enough transport or whatever. And then all of this becomes more complicated.
Yeah, absolutely. So that helps me make an important. So there are two. Amin's point is that this is fundamentally a first order. It really, you have to, it's a first order exercise about the first derivatives. And Christian's point is that it's basically a partial equilibrium supply-driven analysis. Here, the shocks I'm studying come from cost shocks viewed as exogenous. And in a bigger economy, they would be linked. Everything would be, the economy would have all these interactions that are basically being killed. It's an economy killing all those interesting macro effects. So this is really a microeconomics paper about a differentiated oligopoly, which takes the market that this is about as sort of a little decoupled piece of the economy. And the tradition, I guess, is to understand those partial equilibrium pieces and then integrate them into a richer macroeconomic model. So those, I agree with you, and I view those as a kind of it's not orthogonal, but it will be stacked on top of this kind of analysis.
I was wondering, sort of concerning my previous question, that maybe if, for example, prices go up due to consumer demand,
right,
then maybe actually it is true that I'm willing to pay more for my bagels at the shop, but maybe the bagel shop is not willing to pay that much more to this provider, and therefore the science could be the other way around.
Yeah. I think general equilibrium effects could change all the signs. Absolutely.
I'm just going to help you out.
Yeah.
With an example, which is what I might do in my econ. We call it 205. Is you introduce a subsidy. So for some reason, the government is interested in subsidizing one of these goods. So it's not a cost shock. It's sort of a tax or a subsidy on a particular good. And then you're going to want to know, you sort of do these exercises of how that passes through to a particular market, to that particular market. But what you're able to do here, show how it's going to pass through to the whole
exactly.
market.
Thank you. And so I'm going to, and in fact, that's where I'm hoping to get to this little tax exercise. So let me push on in the interest of time. So I because I don't have enough time to tell you about everything properly, I'm going to give you, sorry about this artifact, I don't know what's going on, but I'm going to give you a big overview of everything we can do with this framework, and then tell you as much of it in detail as I have time for. So first, there's this reparametrization gives us a new way of looking at the mechanics of equilibrium. So you can look at, basically, if you're a financial analyst with data about, with a theory of the volatility of costs, you think there's going to be commodity price changes and they're going to affect these firms' pricing, you can try to understand just the physics of how volatility in exogenous parameters translates into volatility in outcomes. And that's obviously going to be shaped by the tendency of the system to respond in a particular way, given by the economics of this oligopoly. So it turns out the maximum and minimum volatility that can be caused by external shocks can be described in terms of the eigenvalues I've told you about. The main exercise in the paper is a tax design exercise where we're going to set up Rachel's exercise of small Pavlovian taxation. I get to subsidize some production and collect that money by taxing some other production. And it's going to turn out that I can, and I hope to tell you this in in some form, at least give you a taste of it, that the principal component basis gives us a much more legible way of expressing that answer and the value of taxation power than you could do without doing this transformation. And finally, and maybe most, in some way, most relevantly to this audience, or most in the spirit of the Simons link between applied mathematics and these applied subjects, as you know, in the recent literature on spectral approximation and the theory of big matrices, there's beautiful results about what you can recover about a matrix with noisy observations of it. That's done a lot in all sorts of machine learning and data science applications and statistics. And so it turns out that because those results like to do the principal component decomposition anyway, we can say things about what you can recover, what aspects of the price response of the system you can recover, even though you have really crappy measurement of a lot of the details of the system. Like a lot of the matrix entries in the D matrix, you might know with enormous noise, and that should be troubling, right? The econometricians can't really estimate these. Amin was complaining that it might not be linear, but even when you assume it's linear, it's very hard to recover, those kind of cross effects in D. So when you measure D with a lot of noise, what can you do? Looking at this way shows us that it's, as far as understanding the economic relationships, it's not hopeless. You can actually recover some aspects of this stuff despite very noisy observation. And so that's the big overview. Let me now try to tell you, well, I will tell you, but I will first put up this incredible thing I saw yesterday. So rather than using quantum mechanics to better understand the complexities of people's style minds, we're going to use quantum mechanics to understand this differentiated oligopoly. Okay, so let me skip. I have an illustration of it, but I think that given the time, the example I don't have time to do an example to give you too much intuition for exactly what these eigenvectors are. Maybe, okay, I can't resist doing a little bit. So we set up a little example where you have three goods, a computer and two peripherals. And the two peripherals are complementary to the computer, but independent of each other in demand. And you can set up that little demand, you can set up that little example picking numbers for the intensities of these complementarities. And you can do the eigenvector decomposition. You can compute the eigenvectors of the demand matrix. And you can see simple, so I'll just explain to you some of what you can read off of this. If you happen to have a cost shock that raises the price of the peripherals, but simultaneously lowers the price of the computer, that might happen because of some type of change in commodity prices. That type of cost shock will transmit 1-for-1 into prices. So even though these guys are separate little monopolists, this particular dimension, this particular cost shock will translate as if it was a competitive market, if you'd like. And then there are other cost shocks, like this last eigenvector. If you had a cost shock proportional to this vector, which is increasing everyone's costs at some ratios, that cost shock is highly attenuated. The price pass-through is only 1/3. So if you're this hedge fund analyst with a theory of exogenous volatility to costs, if you change into this basis and describe the volatility to the different eigencomponents of price, then you can say, okay, if the volatility loads mostly onto this cost axis, that's going to be very transmissive to prices. And onto this other axis, it's going to be very much attenuated by the system. And so that's the kind of thing you can do. And the example is done in much more detail in the paper. But let me tell you about the small tax exercise. Yeah, absolutely.
So, symmetry of D. So it's not seeming like you're using that a lot. So if you had heterogeneous consumers and you just had a diagonalizable demand function, so
orthogonally diagonalizable is enough.
Yeah, but you don't need it. If we're using your orthogonality, you still have the basis, and you can still write. Okay.
Yeah, but if these basis vectors weren't orthogonal, I have the feeling that it would really. The reason I'm not concerned is because I would just do the singular value decomposition, which gives you two orthogonal bases, one for the costs, one for the prices, and everything would look exactly the same. If they weren't orthogonal, I have the feeling that something would go wrong, but I couldn't. But I believe you it might not. But our solution, if we didn't have an orthogonal basis, is to do SVD. But I should have a sharper answer to what would go wrong. Yeah.
I think when it's not orthogonal, the identity doesn't have. The identity causes some trouble. you can write the identity as U transpose U, which you can take out U on
Yeah,
both
so
sides.
we are sort of using that, right? We're using the fact that you can, every time you see U transpose U, that just goes away. And that's what would go wrong in the algebra. But
Because you still diagonalize the matrix.
There would be U inverse.
Generically, you could, it would just be U inverse, right?
Yeah.
You really want to diagonalize I minus D inverse, right? Like, and not D.
Yeah, that's exactly. So it's the orthogonality makes it easy to pass that through. That thing. Okay, so tax exercise. So how much? Who's my timekeeper? 10 minutes. Beautiful. Okay, so here is the very stylized tax exercise that we're going to do. Okay, so we're going to focus on a little tax intervention where a planner comes in. Planner says, look, this market has inefficiencies in it, and I want to make a little marginal change to improve matters. We're going to focus on changes that are budget neutral, which means that if you want, so the thing you'd like to do is subsidize because these guys are underproducing. But in order to subsidize some people, I'm going to make you tax some others. I'm going to confine myself to budget neutral interventions. And I'm going to make the intervention small because the real reason is that I don't believe that I understand this demand system at all away from where we are. And so if we're not doing small interventions, then certainly this first order theory needs to be supplemented considerably with heavy assumptions on what's going on elsewhere. So let's not do that. And we're going to give, we have two contributions. One is a simple micro foundation that gives you a completely specific exercise about a planner who ends up wanting to do a small intervention. So I'm going to sort of set that up as an optimization problem and then characterize the solution, which is what the planner does. And the moral of the story is going to be that the planner is going to collect revenue from low welfare pass-through eigenbundles and use that revenue to subsidize the production of high welfare pass-through eigenbundles. So let me tell you a little fable. Imagine two villages. In this village, all the firms are competitive. So they all source the same inputs at a certain cost and they compete with each other. And so price equals marginal cost. In this other village, it's a monopoly. The firms are all monopolists. There's one firm, let's say, that's a monopolist and it sells the same stuff, but in a monopoly way. What you'd like to do is collect revenue from the competitive village and subsidize the production in the monopolized village. Why? Because the monopolized village is not producing enough goods. And the marginal unit that you subsidize, the first unit that you make because of the subsidy, is still very socially valuable. Whereas in the competitive village, the last unit being sold is actually priced at marginal cost, so its social value is zero. And so this is a good idea from a welfare perspective. The punchline of this tax exercise is that's what you're going to do in this entangled, complicated oligopoly, except you're not going to do it in this physically separated way. It's going to be, the separation is going to come from the change of basis that we did. So the part of the model, both whose cleverness and awkwardness are both due to Omer, so all complaints should go in that direction. I'll tell you the sort of the optimization problem we frame in order to make a well-defined small tax exercise. The way we're going to make taxes small is we're going to introduce a little uncertainty into what happens, and then we're going to make a planner risk averse. So a planner is not going to want to make big changes because she doesn't like risks, and big changes are going to be associated with risks. So a little more precisely, ultimately, we're going to implement some kind of taxes on each good, the per unit taxes that are collected, $1 for each unit of production of this good, and maybe subsidize this other good, $1. But the planner can't set those taxes exactly. Instead, she chooses target taxes, and then the actual taxes implemented are the target tax times eta, which is a random variable with mean 1 and some variance. So on average, she gets what she wants, but there's going to be the bureaucracy is going to do funny things, and she doesn't know exactly how much tax is going to be collected. The reason we do that is because if there's this feature and she's also risk averse, then the cost of making a big tax change is that the perturbations are also big and costly. And so they might cause a big welfare loss just due to noisy implementation. So the planner is going to care about the change. This shouldn't say consumer. I mean, it's whatever surplus you care about, but we're doing total surplus for this talk. So the planner cares about the change in the surplus that she cares about, but in a risk averse way, where she likes it to be higher in expectation and she doesn't like uncertainty in it. And so that X and A is how risk averse she is. So now when we make the planner risk averse, she's going to still be trying to do stuff, but in a modest way, so she doesn't let this uncertainty get out of hand. And so the planner's problem formally is to choose these target tax rates in order to maximize this planner's welfare function. planner's value, subject to net revenue being 0 in expectation. She doesn't have any revenue to, in expectation to spend. And so here's the answer. The answer is that at least when the planner gets risk averse enough, that's where our results are sharpest. What she's going to do is she's going to tax each eigenvector with a pass-through below some cutoff, a welfare pass-through below some cutoff, and subsidize each eigenvector with a welfare pass-through above some cutoff, which you can translate back into eigenvalues. She's going to tax firms up to a certain eigenvalue, and then, or tax bundles up to a certain eigenvalue and subsidize the other bundles. So it's a simple cutoff policy. And the idea is that the revenue collected is equally good, whether it's from a high welfare pass-through or a low welfare pass-through bundle, but the welfare consequences are very different. So that's why it makes sense. We can characterize the cutoff explicitly, and I don't care so much about that, but what I am happy about is that we can write in a quite explicit way the welfare change achieved by this intervention. So as the planner gets more and more risk averse, the changes she's going to make are smaller and smaller. So the welfare change is going to go down. But if we account for that by multiplying back by this A, this risk aversion parameter, I can write explicitly what the Pigouvian leverage is. So we have this formula which says that the Pigouvian leverage is N, that's the number of firms, divided by this number. And this number just depends on stuff about these welfare pass-throughs. So it's just a list of numbers, and you can look at its mean and its cross-sectional variance as a list of numbers. And what I want to emphasize about it is the Pigouvian leverage is increasing in the variance of the welfare pass-throughs. So the more spread apart the welfare pass-throughs are, the more the planner can get out of this little bit of taxation power. Another way to say it is if she has 2 provinces she can intervene in, this one with a big dispersion of mu's and this one with a little dispersion, and she can only do one, then once her A gets big, she'll choose the one with the big dispersion, because that's where she can do a lot by taxing the high pass-through and subsidizing the low pass-through. Time to start wrapping up. As you can imagine, there's a lot more to say. I think the only other thing I'll say is, I don't know that this is such a problem in this room, but sometimes economists say, it sounds like you're happy about this kind of characterization, but these eigenvalues and eigenvectors still don't mean much to me. So can you tell me anything about in terms that are not in your strange eigenvector world? And so there's one thing we were able to figure out. If we come back from eigenland into the original basis, I can tell you one finding about this Pigouvian leverage that doesn't require any of this change of basis. And so the result we have here is that this Pigouvian leverage, which I just told you about, can actually be written in the original terms. Okay, so the only thing I need to use is B, the inverse of the demand matrix, which happens to be the Hessian of the consumer's welfare at the equilibrium. And then Pigouvian leverage has this form, which isn't the world's nicest formula, but it has a very clear implication. So this is nothing, there's no change of basis here. These are just the original, entries of the Hessian in the original basis. And the upshot of this formula is the Pigouvian leverage depends only on basically the total magnitude of demand interactions. So the way I want you to think of this formula is, let's take the curvature of these goods in their own, the curvature of utility in own goods to be fixed. What really matters is this sum of off-diagonal terms of the Hessian squared. And that's saying that what really matters for the Pigouvian leverage, for how much the planner can achieve, is the total magnitude of demand interaction. So if I take 2 systems which have the same sum of off-diagonal Hessian entries squared, and let's say I change the signs, right? So I take one Hessian and I flip all the signs, then the Pigouvian leverage is not going to change. Doesn't matter whether they're complementary.
Signs correspond to the cutoff.
Complements or substitutes, whether things are complements or substitutes. Or if I rearrange exactly whose complements or substitutes, but I keep that sum the same, right? What matters is the sum. So this is like an economic insight, and we have no idea how we would get there without actually doing the transformation and coming back. Okay, so I told you at a high level about the noisy observation and the statistics thing. We get to use the Davis-Kahan theorem to do approximate recovery of some of these eigenvectors when we can't do it exactly. And it turns out you can recover enough to do stuff even when you observe D with a lot of noise. But I think what I actually want to say, I'll conclude here, sorry. So this is the last slide, and it's my mesoscopic manifesto. Our mesoscopic. I'll implicate my co-author. So there was literature on this differentiated oligopoly model. People like Vives and Dixit wrote down simple versions of this model and solved it in a case where all the firms are symmetric with respect to each other, for example. And so I think the status quo is we know how to fully solve and very explicitly describe comparative statics in very simple symmetric examples. And then if you go to papers like Pellegrino's IO paper, we know how to numerically calibrate arbitrarily large economies and say stuff, purely numerically about how big is the welfare loss. But there's something to me that's missing in between, which is that, can you gain some insight despite the fact that your economy has 18 firms which are related in a complicated way? Can you kind of think like a physicist and boil down what's going on to a few sufficient statistics that you find legible? And I think that an aspect of network theory that I really like is that you can sometimes give these kinds of legible statistics like these eigenvectors and eigenvalues, which apply to medium-sized economies with a lot of heterogeneity, and let you relate the intuitions of what's going on in them. Like somehow I gave these analogies between separate villages and the bundles, and that let you use your intuition about simple examples to think about this heterogeneous thing. And that's really the value of the kind of transformations that we're making. So I think that can generate economic insight. And this is, but this is our best attempt to substantiate that point. So that's what I had. And I don't know if we have time for, we don't.
Maybe one question and then we'll, the rest will
We
go
can do it while
flying.
switching. No, the amount you tax is increasing, like it's ranked. I didn't say this, but we can actually characterize the magnitude of these taxes. If the highest pass-through one is subsidized, the highest welfare pass-through one is subsidized the most in this case. So you can write a formula.
And that's a one.
Exactly.
So at the end of the day, how would
You just convert back from you write it in the new basis and then you convert back into the old basis.
Could you also do some normalization, like some row level or column level?
Right, you can undo that, but yes, you'd have to ultimately go back to the basis. Thank you very much.